Hey guys, how's it going, and welcome to today's lesson on apparent weight. We're going to be taking a look at apparent weight in the world of physics and how all that works. So, without further ado, let's go ahead and jump right on into it. But before, make sure you guys, if you want to know any more information on physics, biology, or chemistry, you go ahead and subscribe down below, because you never know when you're going to need some more information on it, and you might just be able to find some more information on that here on the channel. So, without further ado, let's go ahead and jump into two annotations that you're going to need to know throughout the rest of this video. Fn equals apparent weight. Your apparent weight is basically what your weight appears to be given the circumstances of pretty much the acceleration that you're experiencing at any given moment due to a planet or due to a force acting upon you, okay? And so then your true weight is your actual weight given your mass simply by the little g gravitational pull on your body. So your mass times gravity of the celestial body that you're on that's the only thing determining your true weight. Your apparent weight can be affected by different accelerations that you're actually experiencing in time, say if you're going up at a certain speed, etc. So your apparent weight, your Fn right here, is determined by your true weight, your mass times gravity, plus your mass times acceleration. And as a current theme that's going to be throughout this entire video is force equals mass times acceleration, Newton's second law. Ta-da, Newton's second law. Going to be concurrent throughout this entire video. You're going to see it over and over again, really all the time. So, no acceleration. That means that, look at that, F equals ma, already showing back up, aren't you? F equals ma, so that means no acceleration. You're not going to be experiencing any different acceleration than you would already be experiencing from the celestial body that you're sitting on. So Earth is always going to be 9.8, so we're going to use Earth as an example for acceleration for the rest of the video. 9.8, you're not accelerating upwards or downwards, so you can also be traveling at a constant speed. You're not accelerating, you're just traveling at a constant velocity of, say, 1 meter per second, and preferably upwards or downwards is more simple to think about. So 1 meter per second, and you're not experiencing any change in acceleration, which means that this 9.8 is going to be the same. So that means that 9.8 times your given mass is going to equal your force. And as you can see right here, that means that your actual mass, your true weight, is going to appear to be the same as your apparent weight. It will be the same as your apparent weight. So as we move on to the more complicated side of this, and none of this gets too complicated, so don't worry about it, guys. Your acceleration is up, so ma is positive. So remember that as you go up, if your acceleration is upward, it's pretty much always going to be positive. And if you go downward, it's pretty much always negative. That's how you should assume it, unless stated otherwise. It can be flipped. It honestly doesn't really matter. You just have to remember that it's a bunch of sign games, and doing it that way is just the better idea. So A is up, so ma is positive. That means that as F equals ma, there it is again, as A increases and becomes more positive, so will F. That is because m, your mass, should never be negative. That should go to some common sense to you guys. Be surprised if you thought it wasn't. Anyways, the elevator floor and the scale push up on the person to accelerate him with the elevator. That means that the floor is making more contact with the person above it, exerting more force on each other. The scale pushes upward with extra force on the person to accelerate the person's mass upward, resulting in greater contact force, there's the key, between the scale and the person. Therefore, your apparent weight is actually more than your actual true weight. That's because your acceleration, let's say that you accelerated at 1 meter per second, so your F equals ma, instead of the a being 9.8, it's now actually going to be 9.8 plus 1, which is going to be 10.8. So that's pretty simple. Reading on the scale will be greater than the true weight. That's because as a increased, your F also directly varied and increased. So, moving on, going up and slowing down. Initially at a constant speed, moving up in this case. So, as you were going up and slowing down, you were initially moving at a constant speed, which falls back under this principle right here. The elevator is at a constant speed, which means that you are experiencing no acceleration, so your true weight is the same as your actual weight. They equal each other. However, A is downward now and is now experiencing negative variation. So your A, an F equals MA, which is normally 9.8, is going to feel like you're experiencing a subtraction by, let's say you're slowing down at 1 meter per second. You're going to subtract a big old 1.0 from that bad boy, and you're going to get a 8.8 meters per second of acceleration. And so as that acceleration decreases, your F is directly going to vary again and decrease. And so you're going to feel like you have less force. So the inertia of the person would prefer to keep moving up at a constant speed, so the elevator and the floor and the scale drop out a little bit from underneath the person as the elevator slows down. Elevator and the person are moving together, so no floating occurs, but the contact force between the person and the scale is reduced. So the little person sort of floats up a little bit. Imagine if you were going up on an elevator and it started to slow down, you would want to keep going up and you'd feel a little lighter on your feet for a second. That's the scenario that we're talking about. Since the scale pushes upward less force on the person, since the scale pushes upward with less force on the person to support the person's weight, the apparent weight is smaller. That was a doozy to read for some reason. Anyways, reading on the scale will be less than the true weight, given that your F equals ma was varied in such a way. So your actual weight is less than your true weight. Got it. So going down and speeding up. Elevator and person speed down from rest at a higher floor. A is negative. So that's sort of the same thing that just happened here, just sort of inversed. And the way you can always figure these things out is if you think about them. Okay, so when you're standing in an elevator and I start to go down and I accelerate downwards, how would that feel? You feel lighter, just the same kind of lighter as you feel when you're going up at a constant rate and then you slow down. So if you're ever stuck and you're confused, just think of what it would feel like to be yourself in an elevator, and that can help you out with some questions. So A is negative. Again, negative 1 meter per second. It's going to bring us back to the same 8.8 meters per second on Earth. Inertia of the person preferred to stay at rest. So elevator, floor, and the scale drop out from underneath the person as they accelerate downward. Elevator and person are moving together, so no floating actually occurs. But the contact force between the person and the scale is reduced. That's the key part. You're obviously not flying around inside the elevator floating around, but your contact force is reduced. Apparently, it appears to be reduced because of this variation acceleration. That rhymes. Since the scale pushes upward with less force on the person's feet, the person's weight, the apparent weight is smaller. Reading on the scale will be less than the true weight. Your apparent weight will be less than your true weight. So going down and slowing down, this is the same idea as if you were going up and speeding up. So going down and slowing down is the same as going up and speeding up. They sort of connect that way. Anyways, I think you guys will make that connection. It's sort of hard to explain that, but I think you guys understand it. So A is upward and is positive. So F equals ma. There it is again, as A of 9.8 increases by, let's say, 1 meter per second. Now you're going to be experiencing 10.8 as equal to the A. Ta-da! We're back to that. So we're really sort of repeating ourselves from the first half of this video. The elevator floor and the scale push up on the person to accelerate him with the elevator. So again, as it pushes up the person, as the elevator pushes up on the person is pushing back down with them with equal or with as much force as the person can push down on them, and you're experiencing an acceleration. Yeah. Anyways, the scale pushes up with extra force on the person to accelerate the person's mass upward, resulting in greater contact force between the scale and the person. So your apparent weight is going to be greater than your true weight. Why is that? That is because you are increasing A, and as A increases, F will increase. Your acceleration upwards causes A to increase. So reading on the scale will be greater than the true weight. So I can try and explain this in a lot of different ways, but really all you need to get from this is F equals ma. If your acceleration is upwards, that means it's probably positive. So if your acceleration is ever positive, given whatever circumstance it is, your acceleration for Earth is 9.8. If your acceleration from something else is positive, it's going to increase that 9.8 to X amount, and that X of positive, that positive X, which is greater than 9.8, is going to cause F of 9.8, and M, of course, you got to throw the M in there, is also going to be greater than just your normal F, if that makes any sense to you guys. I'm just trying to explain it in a lot of different ways. Maybe maybe some of you guys aren't quite understanding it. So the entire system accelerates downward in free fall. Now this is a new situation. The scale and the person free fall together, no contact force. Normal force between the person and the scale. So normal force is the amount of force that they're pushing back on each other. And so there's no contact force, and the person and the scale falling together. Scale cannot support any of the person's weight. So your apparent weight is a lot less than your actual weight, which your apparent weight appears to be 0, but you actually still weigh, let's say the person weighs 50 kilograms if they're standing on the ground. You actually still weigh 50 kilograms. And so here is just a little, it's a little picture drawing of what the idea of this whole system is. So there you guys have it. If you like the content, make sure to like, comment, and subscribe down below. If you have any more questions, feel free to leave them down in the section down below. Would love to help answer them for you guys, and make sure just to stick around. We're going to be covering more physics in the future. Thank you guys for watching.